Hello. Welcome to the second Minerva Distinguished Lecture Series. As Peter said last time, we're really grateful to Friends Hall Foundation for supporting this wonderful lecture series. And today, on Monday, we listened to Ben's talk about rigidity, about maps between modular spaces. And he actually constructed many correspondences I never heard before. And today, we talk something more exciting. We'll talk about mapping class groups of K3 surfaces from Thurstonian point of view. Then we talk about smooth model V. So let's welcome to Farb.
Thank you. Thanks again for the invitation. Great to be here. I think Peter mentioned yesterday I was a PhD student here. And I just wanted to say one story to characterize Princeton in my mind. I was a first-year graduate student in 1989. I was working on homotopy theory, working with Wucheng Shang. And I'm in the tea room. I had some elementary question that I even forget, pretty elementary. And people said, you should ask Thurston. So I walked up to Thurston, and I asked him my elementary question. And he says, oh, well, do you know the symplectic structure on Teichmuller space? And I'll say, I've just won this award for a book on Teichmuller space, and that's not even the book. That's like really fancy, pretty fancy, and incredibly sophisticated. So of course I said, no. And he said, do you know what a differential form is? And so, yeah, I walked away very, and of course I ended up switching advisors to work with Thurston. Anyway, today I want to, the general series is the following. Basically, the theme of this talk is that the study of mapping class groups, which I'll tell you what it is. In 2020, when we started this project, this is all joint with Eduard Looijenga. When we started this project, basically, it seemed to me, once I found out what was done, the mapping class groups in dimension 4 in 2020 was at the same state as mapping class groups of surfaces, two-dimensional real surfaces in 1973 before Thurston just changed everything. And so one thing that we've been doing is bringing, it's a different point of view than's been done. It's orthogonal, basically, to almost everything that's been done. And it definitely is very much informed by kind of what happens, what Thurston told us about surfaces, which I decided to not actually summarize, but it's in the same vein. And here are 3 papers. One of them that's not out yet, it'll hopefully be out in a week or two, that explain, and today, I'm dividing it into 2 talks. The first talk today, I'm gonna focus in, there are 2 ideas that we use. One that I'm talking about today comes from number theory, that actually has to do with homeomorphisms of 4 manifolds. And the second one comes from differential geometry and moduli spaces. And there's yeah, so it's a lot of ingredients, so let me just start. Okay, the objects. Okay, today it's about 4-dimensional manifolds. I'm especially gonna think about complex surfaces and even smooth projective surfaces, connected 4 manifolds. So this simplifies it, but it's already extremely rich. So M, I'm always gonna make it an oriented, closed 4 manifold, smooth 4 manifold, and I'm going to assume that M is simply connected, okay? And that implies that the standard invariants of algebraic topology, so H0 and H4, since you're oriented, they're both Z, and H1 with Z coefficients always is H3 will be 0, and the second homology, so all the invariants vanish or are standard, H0 and H4, except for H2, and by the universal coefficient theorem, it's free abelian. So that's where the action is, and the intersection, H2 comes endowed with a symmetric bilinear form that takes integer values. And there's 2 ways to do it. If you give me a cycle, it turns out in a 4 manifold, every 2 cycle can be represented by an embedded surface. So if I take 2 embedded surfaces, I can take their algebraic intersection number. So the picture, I'm willing to come all the way here and take the 10 seconds to get Hagoromo. If you have one surface, this is a sketch, of course, and then another, you can look at the number of intersections, but if you orient both things, it comes with a sign, and this orientation, once you fix a background orientation, going from red to white is this, and going from red to white is the other orientation here, and it reflects the fact that if I pull this off, right, if there's no topology here, it's the same intersection number. So the amazing thing about this is to Z, is that this is independent of any choices. And another way to do it is you could also take the Poincare-Dole of S. I mean, you could also send it to, here's another way to get this number, the Poincare-Dole of the first one, that's a form, and you can wedge it, or you can cup it, the Poincare-Dole of S prime, and then evaluate on the fundamental class, and you get the same thing. Okay? So this is a symmetric bilinear form, integral, just meaning it takes integer values, and it's unimodular, which means unimodular, which just means the matrix representing it. You're represented by a symmetric matrix once you pick a basis, and any such thing is has determinant 1, and this is by Poincare duality. So attached to a smooth, simply connected four-manifold, the main, in fact, the only Hatcher-level algebraic topology invariant is this symmetric bilinear form. And so the data, I'm going to call it H sub m as this complete invariant. It's the second homology, which is a free abelian group equipped with a, sometimes called a quadratic form, and this is what people call a lattice. And number theorists just call this whole thing a quadratic form, as far as I can tell, even though it's a free abelian group equipped with an inner product. That's okay. And great. And what else do I want to say before I get on to the main attraction? Yeah, another piece of data. You can look at the orthogonal group of this. It's the set of isometric isomorphisms of the abelian group, H sub m, as an abelian group, and you want it to preserve the inner product. It's an orthogonal group. It's sitting inside. You can tensor everything with the reals, and this is a real semi-simple Lie group. And every matrix like this, non-degenerate, because they're unimodular, can be diagonalized. That's Sylvester proved that. Symmetric matrices are diagonalizable and has a signature. So it's always equivalent to like x1 squared plus x2 squared, etc., plus xp squared minus xp plus 1 squared minus xp plus q squared. That's OPQ over the reals. This is a semi-simple Lie group. And you can see this group is sitting inside here. Sorry, it's called a lattice. Nothing to do with that word lattice. That's mathematics for you. But it's an arithmetic subgroup. It's cofinite volume discrete subgroup. Okay? So that's all the data attached to a simply connected four-manifold. What I want to study, and what is a classical topic, and in some ways has been studied for 200 years, but not in the way I'm going to say, what are the homeomorphisms from four-manifold to itself, or from any manifold to itself? In dimension 2, it's the 1970s and 80s, the work of Thurston and others. Dimension 3, there's some open cases, but it's pretty boring. Dimension 4, there's almost nothing known. I'm going to tell you everything that's known, but you basically just care about what are the diffeomorphisms of four manifolds. It relates to, has other applications, but I'm just going to talk about that. And so here's what I'm going to say. If you consider pi naught of homeo, so you look at the space of homeomorphisms of our simply connected four manifold M, okay? That is a topological group in the compact open topology. You can take its path components. Another way to think about this is the set of homeomorphisms. It's the set of path components. So it's the set of homeomorphisms modulo the equivalence that one is equivalent to another if there's a path of homeomorphisms between them. That's called isotopy. It's a lot stronger than homotopy. But you get a representation to this arithmetic group that just takes an equivalence class of a homeomorphism and gives you the action on the second homology. So any questions? You've converted a topology thing into an algebra thing. You can do this in the smooth category. So it turns out, well, let me just show. So diffeomorphisms, it maps to here. Or if you happen to have a symplectic form for experts, you can look at symplectomorphisms of them and look at pi naught of that. And let me say 3 pertinent things. In dimension 2, these are all equivalent. These groups are all isomorphic to each other. This is not faithful. It has a big kernel. There's a whole study. But in this, there's 3 things. The first thing that happened is in 1986 is the final theorem. I'm just going to say, so there's an amazing theorem. This is an isomorphism. This is part of Mike Friedman's seminal work. And then there are too many other people, including Gabai, who proved, it's a long story that only ended this year, who proved injectivity. Okay? There's injectivity, he proved surjectivity, and there's like Crack, Perron, I don't know, I gotta write Dave because he's here, but Powell and Kirschgall and others. Sorry for the other people. Okay? And let me just point out, so it's amazing. What this says, Mike Friedman's, this was part of his Fields Medal, it says, if you, I should back up 1 second. The first part of what Friedman did, he proved that this lattice, the isometry type, the isomorphic isometry type, determines the homeomorphism type of the 4 manifold. He then applied it to the incredible lattice, the vectors, the lattice 0, that's a free abelian group. The trivial group with the empty intersection form, that's S4. So that's the Poincare conjecture. If you're homotypically equivalent to S4, you're homeomorphic. So we got that. It's still not known if you're diffeomorphic. But this is like a maps version. And let me just say, it's not explicit what Friedman does. So you're given, let me just point what surjectivity means. You're given an orthogonal transformation that permutes the vectors in this lattice. You might have z to the n with the usual dot product. So it's telling you, an orthogonal transformation, it's telling you how you're permuting 2 cycles, which in this case are embedded surfaces. So there's some 4 manifold, M, and if you give me a matrix A in here, it's giving a way to kind of permute all these, not just permute, to map these different surfaces across each other. And you could ask, is there a homeomorphism of the 4 manifold that does that? And the way Friedman does it, he doesn't work with the 4 manifold until the very end. He sort of, it's all this surgery theory and something exists because something vanishes. He doesn't like do anything explicit. But he gets this amazing general theorem. The next part of the story comes here with Donaldson. This is not injective. And that was Ruberman much later. There's like one example, one class of examples where you're not injective. And the simplest is like 20 copies of CP2 connect some 5 copies of CP. So it's very difficult, but Donaldson proved you're not surjective. There exist diffeomorphisms that can't be smoothable, but also there exist, what do I want to say? Oh yeah, if you look at a diffeomorphism, you can't get, it has to preserve something here. You can't get any linear transformation on homology. And here, this is Seidel. He proved not injective. In other words, he proved there's a specific symplectomorphism. For experts, it's a square Verdane twist. It's smoothly isotopically trivial, but not symplectically. That's really hard and delicate. And the field has basically been 50% on understanding other examples and 50% on this. And we're just going to go completely orthogonal. And today, this is going to be the mapping class group. It's just terminology for like modular group. What we're studying is pi naught of diff. Okay? And the goals of our paper, the goals of our project, before I give the goals, let me quickly give some examples to give you a feel for one or two, and we'll see others later. So people had studied I'm going to write it like this, biholomorphic automorphisms. If you have a compact, complex surface, so J is like a complex structure, and you can look at biholomorphic automorphisms. People have been studying that since the 1800s, and even the 1700s in some ways. What are the groups that you can get? But also McMullen, Kurt McMullen, there's infinite order ones that are very special. He has a beautiful paper called Dynamics on K3 surfaces that's in the last 20 years. Another class that people studied that I mentioned, for every embedded two-sphere, S in your manifold, such that the self-intersection number is -2. What I mean by self-intersection number is you take your submanifold and you just perturb it, and by transversality, it'll intersect transversely, and you do the signed intersection. What this implies is that if you take a tubular neighborhood of S2, it is isomorphic to the cotangent bundle of S2, right? In dimension 2, when you take a tubular neighborhood of a loop, it's an interval bundle, and so it's either the Mobius band or a cylinder. Here, it's much richer, but I'm going to assume this, and then you can come up with a diffeomorphism called the twist in S. It's a diffeomorphism, in fact, a symplectomorphism. And it has, in this dimension, it has order 2 in the mapping class group. So its square is isotopically trivial. And maybe I won't discuss what it is, but let me just say it's the time, you take the time pi map of the geodesic flow, or the co-geodesic flow, composed with the antipodal map. And when you do that twice, you get the identity. You have to prove that. I think this is essentially coming from the fact that pi 1 of SO3 is Z mod 2. But it's an order 2 thing. Whenever you see a -2 two-sphere. And that's about it. As far as I know, and I always joke when I give this talk, as far as I know, people hadn't actually tried to write down a diffeomorphism of a 4-manifold, other than like compositions of these. That's a bit of an exaggeration. But the goal of our project is kind of threefold, and it's not just a project, it's like a project that would take hundreds of years. I mean, I think hopefully other people are working, but the big overarching theme is, understand this surjectivity. If you give me an element, for example, of the mapping class group, I shouldn't have said it's isomorphic, it maps to it, it's isomorphic in the topology category, but just give me a matrix, give me an orthogonal transformation, tell me how the surfaces are permuted around in the 4-manifold, find a homeomorphism or a diffeomorphism that doesn't. That's pretty explicit. Just try to write one down. I know that's not a well-defined thing, but you'll see what I mean when I do it. The second is there a representative, if you have a diffeomorphism, you want to try to homotope it to something that has an invariant geometric structure? Does it preserve a foliation, maybe with singularities? How do you tell topologically if a diffeomorphism preserves a complex structure, or it's homotopic to one that does? How do you see that? And other things like Riemannian metric and complex structure we'll talk about more tomorrow, a little bit today, complex structures. And there's this amazing dictionary between kind of the geometry of these lattices. You get like every lattice. So you get like the Leach lattice, the 24-dimensional Leach lattice. There's a manifold that has that as its homology lattice. And how can you see things there in geometry and topology and vice versa? I'll give some examples today. And finally, there are realization problems. If you give me a group of orthogonal transformations, can it be realized by a group of diffeomorphisms? In other words, is there like if you give me a finite subgroup of O of HM, is there a finite subgroup of diffeomorphisms that induces that action? Okay? These are kind of all inspired from dimension 2. And I think none of these questions, I've never seen them kind of asked. But for people who study 2 and 3 manifolds. I joked with Dave Gabay yesterday. I said, why are you, although he's now working in 4 manifolds, so he's got, but I'm like, the world of examples is like 10 to the 10 to the 10 times richer than like 3 manifolds. It's amazing, like the topology that arises. And so that's what I believe. Whoop. Okay, okay. I'm just gonna leave it. It's going to appear. Okay, so, yes. So let me continue with a case study to give you a feel for what we're trying to do. Case study, the rational elliptic surface. When I say I mean in the smooth topology world, there's many complex structures on it, elliptic. I will tell you what this means, but let me first say, so let M be the blow-up at n points of P2, by which I mean CP2. So you take CP2, which I think it's the space of course, complex lines in C3. It's a nice 4 manifold that you take n points, P1 to Pn, and each point you replace by the space of lines at the point. And these are called the exceptional divisors. I will call them E1, E2, and E3. So you've replaced a point by the space of lines at that point, but that's a copy of CP1. P1, sometimes I drop the C, which is of course just the a two-sphere. And just for the record, its self-intersection is -1. And for more topology-minded people, this is diffeomorphic to CP2, connect sum n copies of CP2 with the other orientation. And what connect sum of 2 manifolds is, you take a little ball out of one and a little ball out of another, and now you have a 3-sphere, and then you identify them together by an orientation reversing homeomorphism, and it gives you a manifold. Okay, so I wish you could spend several lectures, and I have, on kind of understanding blow-ups. But now, part of the philosophy, I would say, is let's take Mike Friedman's and the theorem seriously. Let's take all these people's theorems seriously. So what's the intersection form? Well, it's z to the n, I'll call it 1 plus n, because Mayer-Vietoris theorem, if you take CP2, the homology of CP2 itself is generated by a line, I'll call it E0, right? It's a copy of CP1, that generates the homology that's sitting here. And then each one of these has a generator, and it's like Mayer-Vietoris. So E1 to En. And these generate the homology. And of course, what's the self-intersection number of a line? Anybody? What happens when you perturb a line? What's the intersection? Yes. It's 1. 2 lines intersect positively in 1 point. So the QM is given by a matrix of a single 1 and then -1, -1, -1, -1. This comes from E0, E1, En. So any questions? This has signature, it's called signature 1,9. And so the orthogonal group is a well-known arithmetic group, O1n of Z. Okay. And the topological mapping class group is this arithmetic group. And the crazy thing is, this is a discrete subgroup of like O1n of R, which is almost isomorphic, so I'm going to put a little bullet up to index 2, to the isometry group of hyperbolic n space. And it's coming from the hyperboloid model. You take a cone, the points of length 0, and inside the cone, you have the sphere of radius 1, and it has 2 components. And this is the famous hyperboloid model of hyperbolic space. So all of a sudden, you started with the blowup of CP2 at a bunch of points. Has nothing to do with hyperbolic geometry whatsoever. But amazingly, you end up getting this very beautiful and remarkable n-dimensional hyperbolic orbifold. It has a bunch of, for experts, finite volume cusps. And in fact, there's like, it's amazing. The number of cusps it has is the number of positive, definite, even quadratic forms of rank n, maybe plus one. It's incredible what the groups occur, these incredible hyperbolic orbifolds. And so one of our ideas is just to take this seriously, the fact that it's hyperbolic isometries. And so let me focus in on the n equals 9 case. For algebraic geometers, Serafina Lee worked up to the blowing up to 8. Something magical happens at 9. So it's about ampleness of the canonical class. But something magical happens, and we'll see as topologists what happens. But it is a great story for up to 8, and that's Serafina Lee, who spoke here on it a few weeks ago. But what happens for 9? Let me just do this, and then it's going to be the example you blow up at 9 points, and we'll see why 9 is magical. But let me just remind you, we have this representation from the mapping class group. Let M be the blowup at 9 points of CP2. We have a representation to O, 1, 9 of Z that just takes a class and shows how it acts on homology. Okay? For the topological mapping class group, it's an isomorphism. For the smooth one, we know it's surjective. I'll say that in a second, and we don't know if it's injective. Okay? So you look and you remember, oh my God, Winberg proved that O1n up to n equals 17 proved that O1n of Z contains an index 2 subgroup generated by reflections. It's quite miraculous. And here is, I'm not going to go through with my time I have, I'm not going to go through, but the idea is that this is encoding. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 reflections. The reflections in the vector, right? What do you do in a reflection in a lattice? You pick a vector, and you pick a vector v, v perp, it's the identity on v perp, and it takes v to minus v. In order to do that, and to still have a lattice, by the way, your vector v has to be a -2 vector, because if you remember from linear algebra class, reflections in a vector v acting on x takes x, and then it's minus, you take the inner product of x dot v, twice that, v dot v. This is the formula for reflections from linear algebra class. You check that because it does the right thing on v perp and on v. So you can see if I want to preserve a lattice, this free abelian group, you better have v squared equal to -2. V dot v equal to -2 to make it not be a fraction. I think I got this right. Sorry? Yes, oh, so maybe, yes, let me drop that comment. But anyway, so you go here, and this tells us, the first thing it tells us is that the image of the mapping class group is that, at least the topological one, it's generated by, of course, this is generated by reflections up to index 2. By the way, exercise, so this is surjective, I'm claiming that. Here's an exercise. Find the other, there's another diffeomorphism. It's actually order 2. It's a diffeomorphism of CP2 blown up at 9 points, whose image is not in the group generated by these reflections. And it's something that you all know and love. It's not that hard. But then that gives you the whole group. And you realize that if you take a Dane twist, remember a 2-sphere, if you have a -2 sphere, I know we only have -1 spheres over there, but there are -2 spheres in this picture. If you take a Dane twist and you look at what it does to homology, it's an exercise. You can imagine this, a Dane twist around a 2-sphere, it's going to be localized. It's a little diffeomorphism that you do right around, it's supported in the neighborhood of the two-sphere. So it won't touch the rest of homology. And it takes the two-sphere and it takes it to its negative. And so you show this is reflection in the vector S. So all of a sudden you can see that the group is generated by, that doesn't tell you what the generic thing looks like, but it's generated by Dane twists, given index 2 subgroup, together with this other thing. The second thing this tells you is that, well, let me just say, they're up to the action of the orthogonal group. There are exactly two vectors of length 0, v dot v. Right? v2 dot v2, it's e0 squared minus e1 squared. And ei squared is, e0 squared is 1, and ei squared is minus 1. And so it's e0 squared plus, you're adding them, so you get 0. And the other one, check, it's fun. And so I'm going to take hyperbolic geometry seriously. By the way, yeah. Okay. Okay. Take hyperbolic geometry seriously, and just remember, it's a pure algebra, or for people who know hyperbolic geometry, given any A in O19 of Z, or even inside O1n of R, any isometry of hyperbolic space, or let's say sitting in a discrete group, either A is finite order, which I'll talk about tomorrow, not in, but A of V, A fixes a vector. This is the unipotent case, a parabolic case. There's elliptic is the first case. This is called parabolic. There, A of V for some isotropic. V isotropic just means V dot V is 0. So in this hyperboloid model, there's some vector, this is the disk model of hyperbolic n space, and there's a point at infinity, and you fix just that point. In this model, you can see it's an isotropic vector, a vector of length 0, which is sort of at infinity in the paraboloid. And then hyperbolic type, which I'm not going to talk about, but sort of in some ways maybe the most interesting, but we know the least about it, so. Okay, that's just so you can think about this as finite order, parabolic, or semi-simple. Think of, in fact, these are going to be nilpotent, or almost nilpotent, and then unipotent matrices, quasi-unipotent for, and then these will be semi-simple of infinite order. So it's just Jordan canonical form, if you wish. And what we have, I'm claiming there exist two conjugacy classes. In this case, in O19 of Z, you can figure out what are the vectors of length 0, and then what's their stabilizer. There exist two conjugacy classes of maximal parabolic subgroups. So we're still in algebra world. Remember, this whole thing, it's like a dictionary. You have an orthogonal group of a lattice. I'll call that algebra, but it's the geometry of numbers, too. And we have topology world, which is diffeomorphisms. And they're related by this action on homology. And here, it's the stabilizer of V1 and the stabilizer of V2, where V1 and V2 are those vectors. And what's cool, you can figure out what the groups are. So the stabilizer of V1, which we'll talk about today, it has its own story and world. And the stabilizer of V2 has its own story, and the answers are different. And Serafina did the second one. But it's of type E8. So what's amazing is this manifold for 9, it has two cusps. One of them, the stabilizer, I'll just say, it's like the Weil group of type E8 hat. It's the stabilizer of V1, and it's amazing you get this incredible group of order 1 million, whatever, millions. And it's amazing finite simple group, a reflection group. But anyway, okay? So here's what I want to ask you. Here's the kind of questions. I'm focusing in, what is our goal? We started out with the blow-up of CP2 at 9 points. I haven't told you yet why 9 matters. We know that if we want to understand all the diffeomorphisms up to isotopy, this is the main invariant. In the topology world, it's a complete invariant. We want to understand them all. What does that mean? That means you give me a matrix here. It's of one of 3 types. Today, we're doing this type. You're fixing a vector. We're not just looking at one. You may as well look at the stabilizer of the vector to knock out all the cases at once. And now, what I want to say is, can we find what would be the incarnation of fixing a vector in this lattice? What does that correspond to in topology world? A vector itself corresponds to an embedded surface. An isotropic vector, its inner product with itself is 0. What does that mean? Not by definition, but it's equivalent. It means that you can perturb it off itself to be disjoint. That would be one way to do it, right? If I can perturb it off itself, then the intersection number is 0. So I should be, can I find a diffeomorphism that preserves a surface, and when you push it off itself, you can make it disjoint from itself? Even better, what if there was a whole foliation by surfaces? You're trying to get a geometric reason, an understanding of these subgroups of the mapping class group. And great, I'm going to pause that. But if there were a fiber bundle where the fiber, the homology class of the fiber was this, and I had a fiber preserving diffeo and representing A that had that specific axial homology, that would be like a best representative. I mean, that's another kind of, you want best representatives, like minimal entropy, preserving geometric structures, like I said. Okay? So I'm going to leave you with that puzzle for a second, and I'm going to sort of answer it, but in the idea comes from a well-known concept in number theory. I'm assuming that clock is like an hour off, right? Don't worry. So elliptic fibrations and the classical Mordell-Weil group, I should call it the holomorphic Mordell-Weil group. So let me give a definition. An elliptic fibration of a complex surface, just a surface with a complex structure, sorry, a two-dimensional complex manifold. Let me just say what it is. You have a two-dimensional complex manifold. You have a projection pi. I'm going to think of it as CP1, but of course it's like C hat. It's the good old Riemann sphere. It has a unique complex structure. I want this map to be holomorphic. And I want pi inverse of B is a torus, complex torus. I'll write it like that. I know this is a little more data than a complex torus, but is a complex torus for all but finitely many B. And then there's finitely many singular fibers. Of BI is a singular fiber. And Kodaira amazingly classified, it's very beautiful, what all possible singular fibers can be. But generically, you can have this as a singular fiber, a chain of like CP1s. This can be pi inverse of a point. So this is wacky. You can write down an example. You can have over a disk, every point except 0, you get a torus. And it's a complex manifold, and it degenerates into a bunch of these. That's actually not that hard. Think of a torus, and you have a bunch of these things like this, and then you pinch them all down, you're going to get like 3 spheres, each one touching the next. But the generic singular fiber is what's called a rational nodal singularity. It's just a torus with a simple closed curve that you pinch to a point, and that's called the vanishing cycle. This goes way back, at least before Lefschetz even. Okay? And so an algebraic geometry picture of this would be here's CP1, here's M, and algebraic geometers draw this picture. Once in a while you get some singularity, you can get a cusp and whatever, but we're just gonna do this generic case where this is supposed to represent nodal because it's a sphere with 2 points touching. So it's a sphere that intersects itself transversely, kind of see. It is what it is. And here's a topologist version. Here's my, here's an elliptic fibration, but the real points. It's like a sweep out of a manifold by tori, and here it's like sort of real elliptic curves. I apologize, I cannot find who did this. I just had these, and then I can't find it anymore. Okay, but there's a topologist. It's a circle, and then this is my picture of C hat. It's the plane with the point of infinity. Everything is smooth except there are these like 12 singular fibers. And great, let me just give you an example of this. Example would be M is the blow up at 9 points, so CP2. And what you do is you take two cubic curves, homogeneous polynomials of degree 3. They will intersect in 9 points by Bézout's theorem. They will completely sweep out all of CP2. And so you take, if this is the set P equals 0, and this is where a polynomial Q equals 0, a cubic Q equals 0, I can take EST, it's the set where SP plus TQ equals 0. And it only depends on the ratio ST as a point of CP1. So I can write, there's a map from M, it's not from M, you have to, I'll tell you why. There's like a map from P2 to P1 that just takes M to the ST, where ST is the unique. So right, this curve is sweeping out the space. And if you want to know where to map that point, it's which parameter ST do you lie on. However, these are zeros of P and Q, so every one of these intersects these 9 points are zeros of every single one of these curves. They're all complex tori. And so this map is not well defined unless you blow up the points. And what that does, you blow up the 9 points, and it differentiates each of the directions, becomes a different point. So now you get this new manifold. It has a map to P1, and the generic fiber, every fiber is one of these, and it turns out you can check, when does this polynomial, the zero set of a polynomial SP plus TQ, when does the zero set, when is it smooth and when is it not? And it turns out it's not smooth exactly at 12 points. You can ask me after, I have a good explanation for you for 12 singular fibers, and generically they're generic fibers. So that is an elliptic fibration. This is an elliptic fibration. It's this beautiful thing. They don't exist when you blow up 8 points. They don't exist. I have to come up with a cubic curve somewhere, a torus. Okay? So any questions? That's where 9, it's the smallest. You're taking 2 curves of degree 3. You can do the same trick for 2 curves of degree 4. But the fiber, it's a different, the fibers won't be tori. Okay? And what I want to say, I want to define the Mordell-Weil group, the holomorphic Mordell-Weil group, which you can define for any elliptic fibration whatsoever. Damn. Okay? The Mordell-Weil group of an elliptic fibration, I'm going to define it. It's the set of automorphisms, biholomorphic automorphisms of your complex surface, such that F acts by fiberwise translations. What I mean by translation, when you have a complex structure on M, each of these tori gets endowed with an affine structure, so you can make sense of what it means to translate. And this is isomorphic to, when you have a section, officially it's a torsor, but isomorphic to the set of sections, sigma of pi. And without going through a lengthy definition, I will just say this is a really cool thing. Here's a way to get a biholomorphic map on an elliptic fibration. You pick a section, sigma naught. That now gives each fiber was a torus. A torus is not it seems like it's a group. It's not a group. You have to pick an origin. Once you pick this, each one of these gets a base point. Now there are these singular fibers that look like this. This is a group too. It's C star, because it's the sphere minus 0 and infinity. And it's cool, you can see the group structure like degenerating to this. But you take that, and then I take another section, and I can now do fiber-wise translation. Z goes to Z plus, like in the fiber over pi, Z of sigma 1 of B. It gives me a number to translate by, and that plus is in the group structure I get from sigma 0. Okay? And conversely, if you have an automorphism, if you have a section, I can hit it with automorphisms. And so, yeah, I want to get to my theorems, and I'll just say, here you have 9 sections in the blow-up. You have 9 sections, sigma I corresponding to EI, because it's given a parameter point, a point in the base, an ST. You have to tell me a special point. You have to pick out a point on that torus, and I'm picking out this point. This is part of it's the line tangent to that torus. So that gives you a section. And let me just say, this Mordell-Weil group is isomorphic to Z to the 9th. This is, and the general theorem, and the group generated by these 9 sections is not everything. It's index 9. So there's some other really cool thing going on. And there's another thing that I don't have time to talk about called the height pairing, which gives you like an inner product on this. But what I want to say is the classical Mordell-Weil theorem for function fields over P1 which is proved by Lang and Naran in 1959, is that the Mordell-Weil group of any elliptic fibration, holomorphic, Mordell-Weil, is finitely generated. And I believe it's known what they all are at this point. In this generic case, it's like always, yeah. Okay, so any questions? I'm going to give you some more examples. And I'm going to end with showing how this has to do with the Thurston classification, hopefully. Okay. I'm going to define, so here's what we discovered. There's a smooth version of the Mordell-Weil group that is the key to a big chunk of Thurston classification for a big chunk of algebraic surfaces. And let me just make a definition. So if I have an elliptic fibration on any M, I'm going to define the group of translations of the elliptic fibration to be the set of diffeomorphisms now, not by holomorphic automorphisms. F acts by fiber-wise translations. Okay. By the way, let me point out, this holomorphic group, it's a discrete group. And if you do a translation, it's moving one section to another, but they're different homology classes, so you can't be isotopically trivial. And these, in fact, generate a Z to the 9th, the different translations with 9 different sections. But here I'm taking diffeomorphisms. It's a big infinite dimensional group. And the smooth Mordell-Weil group, I'm going to define to be pi naught of the space of translations. Okay? By the way, another comment I want to make. In this paper and in our next thing, so Donaldson introduced like moduli spaces to get the difference between smooth topology and get invariance of diffeomorphism. And we're using Tychelor spaces and moduli spaces, totally different ones in a different way, but we're also getting theorems without using gauge theory. Or maybe we use a tiny bit. Okay, so great, and let me just say what our first theorem is. Okay. So this is not even out yet. So 2024 is that this. So again, the group of all translations, it's just diffeomorphisms. That's a big, uncountably infinite dimensional group. But then you take pi naught of it. It's always finitely generated.
You think it's not a Boolean?
It is. It is a Boolean. And it has a height pairing and everything that I unfortunately don't have time to talk about. But I just want to say one example, class of examples. If I take the rational elliptic, our example, the rational elliptic surface, here's a way to get another elliptic fibration. You take P1 to P1, Z goes to Z to the D, you pull it back, you get a manifold MD and an elliptic fibration pi D. And the way you should think about it is, you're pulling back, and you have, Z goes to Z to the D, there are these D regions, and each one, it looks like what you have on the, it has 12 singular fibers. Sorry, I won't draw them like that. 12 singular fibers. So it's multiples of 12. And I won't take the time to write it down. Moishazan proved that any elliptically fibered, simply connected complex surface that has a generic fibers, it's one of these, up the fiberwise diffeo. So this is a big chunk of examples. M2 is a K, so M1 is the rational elliptic surface, M2 is a K3 surface, which I'll talk about tomorrow. And here's, I just want to state our theorems. We compute the Mordell-Weil group. Z to the 12D minus 4. We actually compute the height pairing on it for the experts. And why I find this really interesting is that the rank, in fact, not even the rank, the holomorphic Mordell-Weil group for any complex structure, any of these examples, with generic, it's Z to the 11D minus 3. And 11D minus 3 is less than 12D minus 4 unless D equals 1. So in the D equals 1 case, the rational elliptic surface, this smooth Mordell-Weil group, every section is homotopic to a holomorphic section. Here it's false. It's false. There's stuff you can't see in the complex world. The smooth Mordell-Weil group is not just some silly generalization of the holomorphic one. You get extra sections, and because of time, maybe I'll just say, well, you can look in our paper for the methods, but it has to be new kind of methods, and what we do is we develop like a relative Mordell-Weil groups, which I'm sure number theorists don't have. Yeah, when D equals 1, did I get the numbers right? Yes.
Why the holomorphic Mordell-Weil?
Oh, because what's happening, the reason is, if you think about it like sections, in fact, I think I drew a picture. Oh, these are cortex surfaces are the case D equals 2. Whoops, I didn't. But I wanted to say, I can explain, there's a topological way of viewing this, where you're gluing fiberwise together two like elliptic, rational elliptic surfaces. And there's something smooth, you have holomorphic guys here, it's like a piecewise holomorphic, but there's ways to glue them that are not. And so the other results that I want to say is that what we have is a whole bunch of theorems, which I don't have time, but I maybe will say them. What I want to say is that let me just give the final picture. This goes all the way back to our yes. Well, let me say what the picture is for this Mordell-Weil group for D at least 2. All of this story ended up being you're the stabilizer of a vector. The vector is the fiber. And that fiber, you can check in this blow-up picture for the irrational elliptic surface, is this, 3E0 minus E1. The 3 comes from the fact that you have a cubic curve. And you're blowing up 9 points on it. So this whole story, we wanted to look at the specific subgroup of the orthogonal group and come up with diffeomorphisms that represented it. Stabilizers, you always map. And V squared equals 0. Right? We wanted to look at the stabilizer of an isotropic vector. It always maps to this. It leaves invariant V perp mod V. It turns out, that this is always isomorphic to V perp mod V itself as an abelian group. It's like Z to the whatever. And so the Mordell-Weil group, one of the theorems, and so this is getting stuff about proving things are not smoothly isotopic. The Mordell-Weil group, the smooth one, it acts on homology. Its image lies in the stabilizer, and in fact, its image lies here, and it's an isomorphism. So we just got a chunk of the Thurston. This is the unipotent radical, basically, for people who know algebraic groups. This is like the unipotent radical. An element here that's not here, here's a cool one of order 2, right? This is a free abelian group. Let me just give you a cool one. Given a section that gives an origin to each torus, I can take the Z goes to minus Z on each torus. Like the group structure, G goes to its inverse, additive inverse. Fiberwise involution, that gives you an element of order 2 in this group. So there's a whole story there. But the thing I wanted to say, maybe the last thing I want to say is, a few things. A first theorem is that we don't just get that this group is Z to the 12D minus 4. We get a group of fiberwise diffeomorphisms realizing this. It's not just a group of mapping classes. It's a group of diffeomorphisms. That group doesn't preserve any complex structure, but each individual one preserves a different complex structure. But as a group, they don't, and that follows from all this stuff. And yes, and maybe I'll just, and if you want a pure kind of topology statement, keep going. A pure topology statement, this group, Mordell-Weil group, is injective, but just from injectivity, you get that all of these different categories are equivalent for this subgroup. This kind of thing for an arbitrary diffeomorphism is really impossible, but this is for this special class. And I want to end with a summary of what we did. Okay, recap. Great. Because we started 1 minute late, so I won't go over. And let me say one other amazing thing that Donaldson proved. Donaldson proved for D greater than or equal to 3, the image of diff, of the group of diffeos, in this huge orthogonal group, O of H of M. This is this tiny subgroup in O of HM. Donaldson proved this is the image of the whole of diff. So our theorem for D at least 3 actually gives like a complete Thurston classification, but it uses this really deep thing of Donaldson. And the recap is we defined a kind of Mordell-Weil group for elliptic fibration. You can think of it as we found a geometric structure. It's a codimension 2. You stabilize a vector. That vector determines an elliptic fibration. Mordell-Weil was the first to notice the term elliptic fibration. But we realized if you had a linear transformation that preserves it, it's induced by a diffeomorphism preserving this foliation, this elliptic fibration, this codimension 2 foliation with finitely many singular fibers. It's a good thesis problem to work out the other Mordell-Weil groups, what they actually are. Each different one, I did the one with generic fibers. Eduard and I did generic fibers, but there are these other really cool ones that give different answers. This is what I just said. And we found invariant geometric structures and other geometric structures that are not invariant. And that's it. I will end there.
Any question?
No, we don't. We don't. And our whole thing that we can do here that they can't do, I think our thing, I mean, there is, there's like a local Mordell-Weil theory where you go around a singular fiber and you just look at like, most of the manifold, a little neighborhood looks like it's just smooth tori, but there's finitely many singular fibers that have some kind of singularity. And that gives a compact four manifold with boundary, right? The inverse image of a point of a disk in the base. And then you can compute a Mordell-Weil group for that. There's a very beautiful picture involving Eichler-Siegel transformations I'm going to mention on Friday. There's braid groups, there's Ricci flat metrics, there's symmetric spaces. There's a whole bunch of fun things. But yeah, so this kind of local and then gluing together using sheaf cohomology. So it's not a shocker. But that kind of method is just orthogonal to everything in four manifold. I mean, yeah, as far as I know. Yes?
When you move by the section.
Yeah, that's a great question. The one thing I left over, the question was, gee, you have these sections, and you're doing a translation, don't you have to worry about the singular points? The answer is, it turns out, holomorphically, it never goes through, and topologically, or smoothly, you can always perturb it off the singular point. But the singular fibers all end up having group structures. Like, this guy is like a two-sphere with the north and south pole. So he has a C-star structure. There's like cuspidal ones, and they have like an additive group structure. There's these, the group C mod 5. I mean, it's really interesting with the groups of diffeomorphisms. And what I love about it is that each different picture, this occurs for surfaces a little bit, but if I tell you, gee, here's a genus 4 surface, sorry. Here's an element of order 4 on a genus 5 surface. Right? If I ask you, give me an element of order 4 in genus 5, it's staring you in the face. But I'm telling you, there's an element of order 22 on this. A diffie of order 22. Go, Dave. No, I'm just saying, there's another picture. You can get this by a 22gon glued together, and then you just rotate. So each different kind of view of the surface gives you like a different picture, a different subgroup of the mapping class group. And it's the same thing here with these singular fibers. Yeah, it's very, very fun. Yeah, how do you know that they're all different? So the first thing was, oh, these translations, the sections are different homology classes. That was at least true in this example because they're different exceptional divisors. And the translation, it's funny, you're just doing something isotopically trivial at each fiber. It's just rotating. How can that be not It's because it's a more complicated global picture. And you do know it's taking one section to another, but they're different homology classes. So you're acting on trivial homology. And then it's an exercise, the different translations are all like linearly independent. Like what's a basis for the translations? And it's like there's 9, so like EI minus E1 is a basis or something like that, yeah.
This theorem is for general, right? Not necessarily just for...
Yeah, the finitely generated is for general. This computation is just for the generic. We only computed the actual Mordell-Weil group in this one case, the smooth. It would be great to compute it. I mean, there's other beautiful foliations, but the singular fibers are different. It's a good thesis project to do. What is that? Oh, yes, I think I'm going to talk about that, yeah. I'm going to talk about K3. K3s came in here, they're the case D equals 2, but I decided to talk about, we realize this is much more general, and this is a really interesting object in a general case, and so that really changed the point of view. Yeah, yeah. By the way, that's a good reason to like, I just want to say like, push things, because the Mordell-Weil group wasn't in the title of our paper, and we were just doing these specific things, and it's like, well, does this work for these other elliptic fibrations, and we have to, and it just kept pushing it until we realized like there's this object, it's just the same as the classical, an analog. Yeah, I think there should be a story there. And in fact, higher dimensions in many ways is easier. Because it's well known that like, dimension 4 is kind of the...
Zero cycles and algebraic surface can have trivial object copy map.
Yes.
So then you get some interesting cycle, which is homology trivial general fiber, but still non-trivial intersection pair.
Yes, yes. Oh, there definitely is a story like that here. Definitely you get these very it's one of the things I was hiding that's a beautiful player in the story, but I'll just say it to the students. If you take z to the 9th, that's an abelian group, with the intersection form 1 and all minus 1s, so like x1 squared minus x2 squared minus x3 squared, etc. That seems pretty harmless, that lattice, with that inner product. But if you take a vector of length 0, E0 minus E1 or something, or whatever, and you take its perp and mod the vector, that gets an induced inner product, E8 appears. So even in these harmless things, you get these, yeah, so I guess, right, number theory, so you call that the height pairing, right?
No, I guess very explicit example, say product 2 elliptic surface.
Yes.
Elliptic fibration over 2-dimensional base.
Yes.
So like I believe you have
Yes. Oh yeah, there's some amazing Calabi-Yales. Yeah.
A and B. First A plus B, then minus A, minus B, then plus 0. This is homology trivial general fiber. But it's not a trivial necessary in this A-dimensional physics.
Oh.
So you get another next level Mordell-Weil.
I would love that. Yeah, I don't know the answer. Yeah. I will say I do believe there's like a famous mystery about automorphisms of K3s, complex automorphisms having to do with the Metu group, this finite simple group, M24. The groups of automorphisms are all occurring inside M24, and it's not really explained. All those different groups, they're different complex surfaces, they all sit in the Mapicness group. And I think I know, well, anyway, there's some interesting things. I think this has potential to say something about that puzzle, and I have more specific things